Hello, I hope all of you are doing well. My name is Shriya Bansal and I'm currently working as a software engineer at Microsoft, and I'm also an educator at pre-level. So now in this video, after having already talked about the concept of deadlocks, we are going to talk a little bit about the concept of deadlock allocation graphs. Okay, so let's quickly get started. So whenever we talk about deadlocks, deadlock can be described in terms of a directed graph. If you have to show a pictorial representation, it can only also be shown in terms of a directed graph, also known as a system resource allocation graph. Okay, so a resource allocation graph can be explained to us like what is the state of a system in terms of processes and resources. Okay, like what all does the resource allocation graph tells us? It tells us about how many resources are available, how many are allocated, and what is the request for of each process. Okay, everything can actually be represented in terms of a diagram. One of the advantages of having a diagram is that if sometimes it is possible to actually see a deadlock directly using a graph. Okay, you don't have to actually apply all the logic and check all the conditions also. Sometimes by just looking at the graph itself, you can tell whether there's a deadlock or not. Okay, but it's kind of like a maybe thing. You might not be able to tell also when sometimes there is a deadlock, but sometimes you are able to tell directly as well. Okay, but definitely the weightage is heavier, right? And the chances are higher that if a system contains a lot of processes and resources, graph is definitely a good way to identify whether there is going to be a deadlock or not. Okay, so how do we really define, on what terms do we really look at this concept? Is that, let's take a look together. So whenever we talk about resource allocation graph, it is mainly a pictorial representation okay of the state of a system. Okay, as the name suggests, it gives complete information about all the processes which are holding some resources or waiting some resources. Okay, so based on this RAG, as the name suggests itself, gives a complete information about what resource, about all the processes, okay, which are holding some resources or waiting for some resources. Okay, not only that, it also contains information about all the instances of the resource, whether they are available or being used by other processes. Okay, so it also gives information about all instances of all resources, okay, whether they are available, okay, or being used by other processes. So you get a good information about that as well. Okay, so in resource allocation graph, the process is basically represented, right? So we have to first take care of a few terminologies also in order to take care of that. How do you represent a process? How do you represent a resource? So let's take a look. So we know we are creating a resource allocation graph. That means it's going to be a graph like a structure, and graph always have vertices and also have edges. Okay. So a resource allocation graph is also going to have vertices and edges. Okay. So in this kind of a graph, the vertices can be of two types. Okay. Firstly, it can be a process vertex or it can be a resource vertex. So processes and resources are going to be represented as vertices. Okay. So first process or first vertex is a process vertex. Every process will be represented by a process vertex, and every resource will be represented by a resource vertex. Okay. Generally, the processes will be represented by a circle, whereas a resource, okay, is basically something that we can discuss in detail, which is also of two types. Single instance resource means it's like a simple box, and inside the box there will be one dot. Okay, so this dot indicates the number of instances which are present for each resource, right? Sometimes there is a resource but multiple instances are present, so that resource can be used by multiple processes simultaneously. Okay, so if it's a single instance, then there is just going to be one single dot. One single dot means that a simple single instance of that resource is available. Whereas if it says multi resources, then it is also going to be inside a box only, but there will be multiple dots present. Okay, so a process represented by a circle, and a resource can be of two types: single dot, single instance; multiple dots, multiple instances. Okay, as you can see over here as well. Process would be something like this, and resource would be like a box. And here, for example, CPU is single instance. Okay, so that would be a simple dot, and multiple instances, for example, registers. How many registers you have available, you will mention that many dots as over here. Okay, so that's what the overall idea is. But this was about vertices. Okay, next we will talk about edges. Okay, now a resource can have more than one instance. If it is having more than one instance, that means each instance will be represented by a dot in the rectangle. Okay, now here, whenever we talk about edges, okay, edges are also of two types. So we've talked about vertices already. Next, we will talk about edges. Edges can be of two types. First is a assign edge, and second is a request edge. Okay, assign edge means that when a process already has the resource assigned to it, then it's a assigned edge. And assigned edge always goes from resource to process. Whereas the other type of edge is a request edge. That means the process is requesting for the resource. Then always the edge is from process to resource. Okay, that means that the process requires that resource in order to execute that request or complete its execution. Okay, so a resource is always assigned to a process if the tail of the arrow, okay, is attached to the instance of the resource. Okay, whereas a process is in waiting state or waiting for a resource if the tail of the arrow is towards the attached to the process, where the head is towards the process. Okay, so if I have like this, something like this, that means it basically means over here that process is requesting for a resource. Okay, whereas if I have a process and if it's the other way, okay, that means that the resource is assigned to the process. Okay, that means the resource has been assigned to the process. Those are the two types which are available. Okay, so we've talked about vertices now, and we've talked about edges as well. So let's actually see an example to fully understand the concept. So here is a resource allocation graph which depicts the situation. So here you can see that P1 is requesting for resource R1. I'll zoom this a little bit. Okay, and R1 resource is held by P2. P2 is requesting for R3, okay, where R3 is held by P3, okay. And for the resource R1, P1 and P2, as there are two instances available, both P1 and P2 are holding the resource R2, okay. So you can see here as well that in this case, what happens is that we have the sets P, R and E. These are the three, I would say, types we have present. P stands for all the processes, which is P1, P2, P3. R stands for the resources, which are 4 resources. E stands for the edges. So we have an edge from P1 to R1, P2 to R3, R1 to P2, R2 to P2, R2 to P1, and R3 to P3. Okay. And in terms of instances, we have one instance of R1, one instance of R3, two instances of R2, and 4 instances of R4. Okay. And again, like I just told you, what are the process states? Process P1 is holding an instance of R2. Okay. And here it is also waiting for resource R1. Come to process 2. Process 2 is holding a resource of R2 and R1. Okay. P2 is holding a resource of R1 and R2 and requesting for R3. Whereas process P3 is holding an instance of R3. Correct? That's what the overall idea is. Now here, what you will notice is, let's go this back. Now here, what we know that the given definition of resource allocation graph, it can be shown that if the graph contains no cycle, then it means that no process in the system is deadlocked. If in the resource allocation graph, you can show that no cycle exists, that means no process in the system is deadlocked. Whereas if the graph contains cycle, then there may or may not be deadlock. Okay, so the idea is if there is no cycle, then there is no deadlock. But if there is a cycle, then there may or may not be a deadlock. Okay, if it is no cycle, that means definitely no deadlock. But if there is a cycle, then there can be a deadlock, there cannot be a deadlock. So if each resource type has exactly one instance, okay, agar har resource ka I just have one instance, and then a cycle implies that a deadlock has occurred. But in this example, you will see there is a resource, right, which has more instances. If the cycle involves a set of resource types, each of which has a single instance, then that means that the deadlock has occurred. Okay, it's more or less like this, that I have one single dot. One single dot means that a simple, and then a cycle implies that a deadlock has occurred. But in this example, you will see there is a resource, right, which has more instances. If the cycle involves a set of resource types, each of which has a single instance, then that means that the deadlock has occurred. Okay, it's more or less like this, that P1, P2, R1, R2, single instances available, sorry, circles. And this is happening. Single instances available and there is a cycle. That means deadlock is bound to happen. And that means every process in the cycle is deadlock. In this case, a cycle in a graph is both a necessary and a sufficient condition to prove as well that there is a deadlock. Okay, if all the processes are in a deadlock, if all the processes and the resources are in a cycle, and secondly there is a single instance of every resource, then that is a necessary and a sufficient condition to prove that a deadlock exists. Okay, but if the resource has several instances, then a cycle does not necessarily mean that there is a deadlock. Okay, if it was single resource, single instance for every resource, then it's a cycle, and a cycle, deadlock. But if there are multiple instances, then there may or may not be a deadlock. In that condition, a cycle is a necessary but not a sufficient condition to say that a deadlock has occurred. Remember these points, they are very, very important. Okay. So to illustrate this concept, what we do is we'll take an example over here. Okay, here we will first understand the resource allocation graph over here. Okay, so that here you can see that there is a process P3, okay, which is requesting for an instance of R2. Okay, and since no request is currently available because there are two instances of R2 and both of them are being currently occupied. At this point, we can say that P3 to R2 is a request edge. Okay, at this point, there are two cycles that exist in the system. Okay, one is from R2 to P2 to R3. Okay, this is the, yes, correct. R2 to P2 to R3 to P3 and then back to R2. Okay, that is one cycle. That means this cycle, this, correct. Follow my cursor, this cycle. And the second cycle that exists is P2, okay, to over here P2 and okay, yeah. The second cycle that exists is P1 to R1 to P2 to R3 to P3, okay, then R2, R2, yes, and then P1. So it's more or less like this. There is a cycle which exists in this format, if you will see the graph, and there is a cycle that exists in this format, which is follow these two markers on this graph and you will understand what cycles are existing. So there are two cycles over here. Okay, suppose, here we can say for sure that processes P1, P2 and P3 are deadlocked. Okay, why? Because process P2, okay, over here is waiting for R3 on the top, right, which is held by P3. Okay, and process P3 is requesting, right, and is waiting for P1 and P2, okay, to basically release the resource R2, okay, whereas already P1 is requesting for R1, okay, P1 is requesting for P2 to basically get the resource R1. So P1 is dependent on P2, okay, P2 is dependent on P3 and P3 is dependent on both P1 and P2. So in this case, a deadlock has actually occurred where a cycle is as a condition has proven that there is a deadlock actually existing. So just by looking at the resource allocation graph, you can sometimes prove, right, that there is a deadlock or not in the entire system. Let's take a look at the next diagram. So here, consider this figure. In this example, we have a cycle. Okay, there is a cycle. However, there is no deadlock over here. And understand this very clearly. Here, the process P4, okay, so here see, there is a resource R1 which is held by P2 and P3. Okay, here there is a resource R2, okay, and which is holded by P1 and P4, and P3 is requesting for it. Now here, if you will see that P4 is holding R2 and it is only requiring R2 only. Okay, so by the time the P4 process is done, and there is a cycle also from R2 to P1 to R1 to P3, this kind of a cycle is existing. And here, if you will see, if somehow P4 requires R2 and it has R2, so after the completion of the process P4, it can release the resource R2 and then P3 can basically take it up, right? P3 can basically take up that resource and hence the cycle is broken, correct? Let me show you in like a representation over here as well. P1, P2, P3, P4, P1, P2, P3, P4, and here we have this, and here we have a resource, this. Okay, now there is this arrow, there is this arrow, there is this arrow, this arrow, this arrow. Okay, now P4 basically requires R2 and P4 has R2. So once this is done, the resource will be released and the process P4 is completed. Now P3 is requesting R2 and there is an empty instance of R2 available. So in that case, this will get converted into this. Okay, and hence you can see already the cycle is broken and there is no more cycle existing in the system, which automatically means there is no deadlock, because we already concluded that if there is no cycle, then for sure there is no deadlock. Okay, So hence, this was a situation where there was a cycle which was existing, but there was no deadlock. That is why we said in the start that the existence of a cycle may or may not mean that a deadlock is present. Okay, so that's what the overall idea is whenever we talk about resource allocation graph. And trust me, I cannot stress enough on the importance of how useful resource allocation graphs are. They are easy to make, they save a lot of time, and they have turned out to be very, very useful in complex situations. Okay, so always make sure that you understand. I would recommend take some examples, right? Take some more examples of some situations and some like resource allocation graph from the internet. Try to make one, right, from different situations, and then try to see by making the one, can you detect a deadlock or not. Okay, and please remember all the conditions which are necessary. This slide number 10 actually talks about a very important and deep points about resource allocation graph and what conclusions can you draw from it. Okay, so this would be it for this video where we did talk about resource allocation graphs in great detail. Okay, and now I think we are actually ready to step on and move to the very next aspect of handling deadlocks. Okay, we'll discuss about 4 different, completely different and equally useful strategies which can be used for handling deadlocks as a situation. So let's take this up in the next video. Till then, keep practicing and keep taking a lot of examples to actually understand the topic in great detail, and I'll see you in the next video. Bye.